So 1 minute for opponents to challenge the problem.
Okay, we would like to change problem number 8, another magnetic application. Reject.
对，因为它的条件，所以这个稍息进行。但是
他把它we would like to change problem number 11.
Answer right?
Yes.
Accept.
，Can you write down your name?
好，13号。
不听听不懂。
另外，另外是，
他们的朋友，哎，我们没有，
我的，
没有，我们在这里。
最高压这边多少？
还有那个，还有
sorry， OK，
好，
可以吧？
Okay, time is up. Please.
Hello everyone, this is our report about the pumping straw. I'm from Winnie Senior High School. It's an introduction first. It's a problem statement. A simple water pump can be made using the straw shaped in a triangle and cut open and the vertex. Inside the triangle is partially immersed in water. The vertex is rotated around its critical axis. Water may flow up through the straw. You can investigate how the geometry and other relevant parameters affect the pumping speed. And the right side is for video. Okay, for the limitation of the problem, we only consider the normal round-shaped straw, and the connect plate is smooth enough to flow. That's quite big, and the straw is symmetrical to its vertical axis. The hole is cut vertically, and the vertical axis is placed into the water vertically. And the pumping speed, the problem actually investigate, is we define the mass flow rate, the dm over dt, where dm is mass of water pumped out by the straw. And this is a picture about how this pumps the water. It's our observation. The picture shows the top of the water is not filled with the water. The surface is here and here. And so the mass flow rate will much smaller than the dm over dt is equal to 2 times by the area of the straw hole and times by the velocity of the water pumped out of the straw. Okay. And let's go into our background theory part. To analyze the motion of fluid, I use the Bernoulli's principle. Okay, to introduce our Bernoulli's principle, the mechanics energy per volume is like here, and plus P equal to a constant. But when we do our analyzation, we set a coordinate system on the triangle straw related with the triangle straw. We're simplifying the analyzation. That is, all the fluid will receive a centrifugal force outward. So we need to add an equivalent gravitational potential energy to this volume. Okay, this is the calculation. We know the centrifugal force for volume is rho r omega squared, and we do the integration and get the centrifugal force, centrifugal potential energy per volume. So we write the calculation like this when we ignore the viscosity. Okay, with these background theory, we go to our investigation. Okay, we first do the experiment the velocity to the straw, experiment the water pumped out of the water and pumped out of the straw. The velocity and the mass flow rate. Per 1 second, the amount of water pumped out of the straw and the model and create a model that can explain the mass flow rate we measured and wrote down the investigation. Okay. First is about our device. We use electrical gel to control the angular velocity, like this. And here, and here is the video. Okay, and the angular velocity we control and measure with the slow motion of the take by phone. And okay, there are 4 sides of throws, and the radius of basis is like this. Okay, we go into our this velocity of the water part. We use the parabola function of the water out of the straw ignore the air resistance to calculate the velocity of water shot out of the straw. B, the x direction is equal to vt cosine beta, and 0 equal to h naught. H naught is the height of the water pumped out of the straw, and plus v. Vt sine beta minus gt squared divided by 2, and we measure as the water pumped out of the straw, the distance, and the beta is the elevation angle, and the h naught. Okay, after solving the function, we can get the velocity. Okay, we measure the h naught x by ruler and determine the flow point of the water, beta, and the beta and the angular velocity of the pump. We find the relationship between the velocity of the water shot out of the straw and the angular velocity. And we can observe the angular velocity increase. The distance of the water pumped out of the straw also increase. And then, so we can know that the initial velocity also increase. And our part is the data. And the error line is about the system error, not the uncertainty. Okay, we need to compare our experimental data with theory. Okay, we used the theory figure before, and with these formulas, E, A, like this. So we call the left side E function, and with some like this, E function of D point is equal to E function of A point. So we can get the velocity of the D point at the inside the straw, the velocity inside the straw. Okay, let's do some math more accurate. We as the water is pumped out at the outmost point of the straw, we consider R is at the outmost point of the straw, and H is equal to the outmost point of the straw, the distance between the water surface. Okay, then we compare our circle prediction with experimental data, and it has a big arrow between the leaves. So we need to consider there are something we didn't consider. We observed that okay, then air resistance. We use the formula of a small ball, air resistance of the small ball, and found that it should be much smaller than the gravity force. Okay, so alright, next. Then this is the surface tension force. It acts in the stroke. We think it's much smaller than the gravity force, so the surface tension can ignore it too. Okay, and the viscosity force, but it is also much smaller than the gravity force. But in spite of this, we thought when the water flows into the straw, it will receive a significant viscosity force we hadn't considered, because the velocity of water flowing inside the straw, when it flows inside the straw, the water contact the straw wall. The velocity of the water contact the straw wall should be 0. Okay. Let's go into our mass flow rate. We measure the mass change by time. Okay. We consider 5 parameters. Okay, then so the straw and the elevation angle, radius of the straw, the depth of the triangle we put into the water, and angular velocity of the straw. Okay, first, the depth of the pump doesn't show a significant relation between the mass flow rate. And the lower elevation angle will cause a higher mass flow rate. And bigger straw makes the mass flow rate higher, and when we increasing the depth, we place the straw, we observe that the mass flow rate also increase. And we need to create a model to explain that. Okay. And how to smaller angular velocity. Also won't impact the pumping speed. Okay, that's a model, and these are some background knowledge. We thought about the flow part inside the stroke on the same streamline. We defined the this is the yellow part is the water surface, and the black part is the flow part. We thought about the flow part inside the stroke, and on the same streamline velocity inside this part should be a constant. Okay, we consider and next is the uniform viscosity. We consider a rectangle parallel to the streamline, v direction. A half root square plus rho gs minus like this is the E function, total energy per volume. Because there's no viscosity and net force on the u direction, cause the water only flow on the v direction. So E point of B minus E point of A should be like this, and as velocity of B is equal to D and A is equal to C. We can see that when we do the math, and we can show at the same streamline, E function of B point minus E function of D point is equal to E function of A point minus E function of C point. And we know the E function also represents the energy. And so the E function of B minus E function of D is the energy consumption during this process. So the energy consumption during CA and dV is the same. That is, the viscosity is a constant in the flow part. Next. When the water is flowing into the straw, our part will receive the huge viscosity force, making the velocity something satisfied at a constant viscosity. Assume that the central part won't be influenced by the huge viscosity, but water flowing into the downward hole. Okay, and we see, and it's a water surface, and here is the threshold point. The pressure of threshold point should equal to P naught, and the acceleration will be 0 there because of these relations. Okay, and consider the E function of B. Is the central part, and is vertical to the threshold point, and we calculate the velocity is also like this. Okay, then the left force like this, and do some math. We know the V of V function, and V of the V point, and the V of the V point is equal to V naught, and we calculate like this, and we can calculate the dm over dt is like this, but we need to time a half because as the mu Lagrangian of V is a constant, we need to times the half to make an accurate prediction. And we found the model test data, but there's a half passive cell here, so it will cause an error. And for the evaluation angle, it also fits, and for radius of straw, it also fits, and fits. Okay. Okay, I come to our conclusion. The formula of the mass flow rate of the pumping stroke, as we define, like this. Okay. Thanks.
2 minutes for the opener to ask question.
Okay.
So I first want to ask you that, do you think that the pumping speed remains the same during the whole stream?
Right, but I do the velocity first.
So then, do you consider the whole motion as a continuous motion?
Whole motion.
Just like the water is continuously flowing up.
Right, it's continuously.
So I want to ask about after the water is being pumped out, what is the distribution of the water?
Distribution. Yes. I just saw the water pumped out, and we set the coordinate system on the pump on straw, and it's pumped out, and we can calculate the initial velocity by the distance.
So you talked about viscosity, right? So do you consider that the wall of the straw and the water drop storm resistance?
Droplet.
Yes.
No, and I'll show that there's no droplet, but there's a lot of water here, and it does have a viscosity. Okay.
So please turn to page 15.
Okay.
So could you please explain more about the E formula? E function.
These two is the mechanics energy of the these 3 is the kinetic energy plus the gravitational energy plus the energy caused by the centrifugal force per volume. Okay.
Okay, thank you. That's
All right. Thank you.
3 minutes for generation. Okay, open it. You have 4 minutes for speech.
Okay, so I'm the opponent from team Faculty. Today I'm going to talk about number 11 compound. So the summary of the report is the reporter uses Bernoulli's principle to explain why the water is being pumped out, and he also used projectile motion to calculate the velocity of the drop, and he also considered the air resistance between the air and the droplet, and he also considered the surface tension and the viscosity. And the conclusion is master formula considering viscosity, length, and several other parameters to calculate the exit velocity of the droplet, which matches in theory. So here are some strengths and areas of improvement of the reporter. So the reporter has a good theory explanation, and he also has some simple and clear diagrams with adequate explanation through his presentation. And he has considered numerous parameters such as air resistance and viscosity, and he calculated a master formula. However, there are some points of concern where the pumping speed should be defined as volume over time and rather than mass over time. And he also lacks an actual experimental data. And I think also he's kind of too focused on his theory. So these are our points of discussion. About the problem statement part, we will talk about the pumping speeds definition, which I mentioned before. And we'll also talk about his experiment methods. So, such as how was the rotation speed constant during the process? And because the water height and is changing, so resistance should be changed with this. And about the experience part, I will ask him about the droplets and whether it's a continuous motion, and also the distribution of water being pumped. So let's start the discussion.
Please.
So the first question I want to ask you about the definition of pumping speed, why you choose to use mass over time rather than volume.
I thought it's not important, but I choose the volume over time or the mass over time because the water is not easy to change their density. So I think when we know the mass flow rate, we can know the volume flow rate. So I thought it's not quite important.
Okay, so next part, I want to ask about your experimental setup. So please go.
Okay.
First, I want to ask you that the edge of your straw is which shape? Assume that the straw looks like this. So I want to ask you that if your straw is this part is parallel to the ground or sideways.
I said it's vertical cut. No, vertical cut. It's like this.
So I want to ask you about controlling the pumping speeds because you mentioned that you use an electric drill. So how precise should that be when you use it electronically?
Contrast the electric drill and this is the bottom. And I made a sticker and like this sticker and we press the button and until the sticker is like this. We can't press the button anymore. So the pumping speed will be set, and the force of the electric drill should be very strong. So I thought it won't be moved by the force of this one.
Okay, so I want to ask about the distribution of droplet that I mentioned before. So as you're doing the experiment, water is coming out like this. Is this an airflow or just droplets?
Like
about airflow, water.
And water flow is here, and it's most at the outmost point. We can observe at this. We can stop. Right, we didn't press the pause button to see.
And as you can see from the video, it looks like droplets coming out of the straw. Separate. This
right. In first, we think that here is full of water, but outside, because the surface tension or hot, it became the droplet.
So this should not be a continuous motion, right? The droplet for the droplet.
Here should be the continuous motion, but not here.
So does the Bernoulli's law is suitable for this part, or is just the reason for the water?
We didn't use this part for
So you just talked about
we
whether
hadn't
water
used that. We hadn't used that.
So I have another question.
And another thing I want to say is, even though at the outside, when we only consider the gravitational force, and this plus this should be should be zero.
So I want to ask you about you used projectile motion to analyze the velocity, right?
Right.
So assume that there is, so water comes out like this. So
Right.
you mean that you calculate this R right here to get the
None
value.
is here. It's here.
Okay, so I assume that here is a straw right here, and this is the axis, and it's spinning at velocity. And it should form a circle of the drop of the water, right?
Right.
So I want to ask you if this circle right here is a range or it's just a circle of water. It should be a range.
It's a circle of water, and the strength is it's well that it's
So it should.
not quite
So
big.
it so I should mention the water being coming out should form like a ring. So
Yeah,
I want
very
curious about which part did you count as R? Is the widest part
The central part.
the central part ring? Okay, so I assume that the droplet should be pumped out from this direction rather than this direction because it is spinning. So it should be there at an angle. So why did you calculate this part? Because this part is not equal to this.
We don't need to we set the coordinate system with relating with the pump. So when we see in this coordinate system, the motion should be like this. It's 2 dimension, not 3 dimension. That's why we say we simplify the analyzation.
Okay, so I want to ask you about if the rotating speed remains the same during the pumping process.
Right, it should be.
But the water resistance did you consider?
The electrical flow is very strong, so it won't be influenced by this.
But as the inverse depth is decreasing, but the rotating speed should have a little bit of difference.
Rotated speed.
Yes.
Rotate.
Yes, the rotating of the omega is very strong.
As long as it shouldn't, because the electrical gel won't be influenced by this. We observe in video the electrical gel is very strong to maintain the angular velocity.
Okay, so then do you assume that your pumping speed remains the same
Right.
during the whole process? So if I draw a graph like this. This is the T and this is the pumping speed. So do you mean that it forms a straight line?
It will drop a little bit, but I only spin for 10 seconds, so the change of depth is not quite big. It's not quite big compared to the depth. Compared to the depth. Actually, I do consider this in the data, but I didn't show that for because of the time. Right. The blue point is we didn't consider the depth drop. This decrease of the water level. We didn't consider the decrease of the water level. But when we consider the decrease of the water level, we should do a small fix. That when we count for 10 seconds and we times by the dV over dt, and we can know how much of the volume we pump out of the pump out. So it will be like this, and this height is about smaller than 1 centimeter. But I thought in this process we can use the depth is the middle of these two, and we think if in this situation we change the depth of the straw immersed in water versus the maximum rate. We first measure it's like 0.15 meters, but at 0.015 meters, and this is about 0.00 like 6 millimeters, and we minus 3 millimeters to this initial depth.
Thank you. So what do you ask you? Did you do a experiment about the angle of this one?
We did. Yeah. But one data is not quite fit.
So
Fit out.
you find that your angle is angle right here or
No.
half.
Here.
So to change this this angle is increasing, so it means that the height of the straw will increase. So how does that affect the pumping speed? And you change the angle.
For non-conductivity sake, we'll say that the centrifugal force is received is stronger if we increase the beta.
So can you draw the force right here?
Okay, we did do that. The force per volume is rho r omega squared. And if we increase the radius, or say decrease the beta, the centrifugal force will increase.
So next question is, so your pumping speed is mass per second, so
Right?
you calculate your pumping speed with this velocity times this area. right here.
No. We're doing that because it will be like this. So it's too hard to consider the area here. We consider is here, and we know by the uniform viscosity, and solve the mu, the margin be equal to a constant, and we can find the mass flow rate. And the velocity we consider v naught is here.
Okay.
Okay.
So as you, I want to go back to discuss about angle. So as you increase the angle, do you think that the moment of inertia will affect the pumping speed?
And then,
Because as you increase the sorry, this will increase, right?
so you think it will influence the electric flow and make it
Do you think that it will affect your pumping speed?
No, we didn't observe that. We done our experience with taking video, and we didn't figure out any angular velocity drop.
So that means that you observe the angle through the whole process. You observe the omega through the whole process.
Right.
You have video. So you think that the omega remains the same?
Right. Because the electric flow is very strong, it's hardly change the angular velocity.
Okay, so I have
Time's up.
Please.
There's 1 minute for the opening to someone.
Okay, so basically first I asked him about why he chose mass over time as his definition of the pumping speed. And then we discussed some points about his experimental setup, which is about the electronic drill and whether the depth will affect the rotating speed. And we also talked about the water droplet after being pumped out. It should be a watering can rather than a trickle. And the rotational speed, the reporter said that the change of depth is not that big for to influence the electronic drill. And lastly, we discussed about the parameter, which is the angle of the straw, and whether the moment of inertia will affect.
Thank you. So now it's time for the reviewer to ask a question.
Okay.
Okay, so the first question is for the reporter. I would like to ask how can you explain more about what causes the deviation in the theory? Because in the graph, I still see the difference.
Okay.
Is there any possible reason that causes the deviation?
It's the ancient I didn't understand how to do it.
That causes the differences in your theory and the experiment. Yeah.
You say velocity or mass over rate?
Let's say it completely.
Okay. for the velocity, it's caused by this viscosity. So the velocity on the edge will be much smaller than in the center.
What about for the other parameters?
Other parameters are big. Okay, I need to. First is here is a mistake. When I stick the straw, there's a silk here. So we think it will much increase the viscosity and the form of the velocity.
Okay, so what about the opponent? What do you think about the deviation in this presentation?
For the equation, I agree with the reporter because there's not seem to be a flaw in this equation, but as for the real condition, I don't agree because I think there are other parameters out there.
Okay, so back to the reporter. I would like to ask, you see, what does your theory count on for the boundary condition? Boundary condition, count condition. Yes.
About meso rate or velocity.
For the water to come out of the straw. How does that account on your theory when the velocity, when the escape speed is low enough for the water to come out? Because there should be a boundary condition.
Boundary.
How does that come?
Okay. I'd like to calculate here, and B is equal to R squared omega squared equal to 2GH. Is equal to 0. So it will be a boundary. So R squared omega squared equal to 2GH. Where the R is the radius. Radius is the distance between the axis and the outermost point of this straw. Outermost point of the straw. And omega is the angular velocity because it is spinning. And the M is the height.
2 minutes for preparation.
As a function of more active.
Okay, so yeah. And for the review of the recording, the presentation, we can say is that the presentation is very easy to understand. And for the theory and simulation, we can say that you have a very clear basic idea. And you did mention the theory limits. However, you didn't show whether the water comes out of the straw or not. You didn't show the specific boundary point because as the statement says, you have to find the water may flow out of the straw. So I think it's important to find boundary conditions for that. And for the for the setup, you did the water velocity, and that setup is pretty clear. But however, you didn't discuss about the shape of the cross section. And for the data analysis, you did the error bar. However, you did not explain details about the deviation. And for the review of the opponent, you have a pretty clear presentation style. However, your opponent is not so quite comprehensive. And for this short question, you did point out some points, and it's short and clear. That's a good thing. However, it comes a bit fuzzy to the terminology. And for the later discussion, you did point out some crucial points, and you have a really nice discussion style and flow. However, you wasted too much time about understanding what they're doing, and you're too focused on the theory rather than other opinions. And as for the key questions, the opponent thinks that the droplet is formed after spitting out of the straw, concludes the Bernoulli and shouldn't be in the outer. As for the reported, it thinks that the continuous flow in the straw. And in our opinion, as a reviewer, the motion outside is not the main focus of the problem. It should not be, it's not connected much to the motion inside. And and the opponent thinks that the 3D analysis is needed for water to drop on the ground. And you should conclude a 3D info needed. However, and for the reported, he thinks that the water outside straw is 2D. And for us, 2D model is supervised, but but you still need the full information about the water on the ground. As for our question, so I will ask, where does the deviation comes from? The theory, and reporter says the velocity of the setup, which is that formula. And opponent says that the velocity and other parameters. And for the problem mentioned in the water may come out, so about the boundary conditions, the reporter takes out when the angular velocity is Thank you.
Conclusion from
Okay, this is our concluding remarks. The water is already pumped out of the straw and will not be a continuous motion, but water inside the straw does. So the noise flow was useful in the straw. Not only used, but it's useful in the straw, right? Okay, the water resistance will influence the rotation since the electrical is very powerful. They can be proven by the video. We control angular velocity. And next is we need to find a better way to control and make sure the stability of the rotating speed. The electrical field is strong. However, this will influence a little. So we need to decrease the error. So we need to find a better way to control. And we should do the measurement of radius of the water ring better by measure for more times and do the average of inside ring and out inner radius and outer radius. Okay, and we should measure the mass flow rate changing by time more accurately. Not saying that 10 seconds is very small, so we can ignore the depth differences. And for the deviation, R squared omega squared is equal to 2G as B is equal to 0 here. Okay, R is and value is here. Okay. Okay, these are our concluding remarks. Thank you.
Thank you very much. So now it's time for jury to ask the questions. Please.
Yes, I have a question for three of you, starting from the reporter. Obviously, you have a pumping machine And when people ask you what is the mass flow rate of the pumping machine, don't you think usually we are concerned about, how heavy or how large the volume of water is per minute coming out of the straw?
I think it is.
Yeah, so if you agree, I bet the other two agree with these arguments, right? But it seems to me your pump flow rate is not that, I mean, experimentally, you are not trying to collect water.
Oh, I measure the weight decrease in the original basis.
Oh, you did?
Right, I did do that, so I can get the mass flow rate data.
Oh, okay, I didn't hear that probably.
Okay, sorry.
Maybe, actually, I just want to ask you, did you keep the rotation speed always constant, or you have to try the different rotation speed?
Because the actual is the force for the torque should be very strong. And because it's I can change the angular velocity during the daytime. I can show. Can I show the angular velocity and angular velocity? Not angular velocity, sorry.
Have you ever considered what's the minimum rotation speed that would have the water out of the floor?
Yes. I'll review it again. And this is H and this is R, and according to our calculation, the E function, the energy of water, is most okay, like this, and R squared omega squared is equal to 2.
I have another question. Because because you are weight the whole system, right? But the water level is keep constantly lower,
Right.
right? Have you ever considered that your straw, actually the length of the straw is increasing in time?
Is that the depth? The depth of this depth of the straw immersed in water is decreasing.
Yes.
Right, but it's not quite big because we just did the experiment for 10 seconds.
Okay.
Okay, so it's not quite big, so we can do. But we do consider in one single experiment because in this experiment we measure the mass flow rate and by time.
I have a question for reporter and open. And actually, during your discussion, it's quite difficult for me to understand what would be the most important parameter to affect the pumping speed. So I would like to ask it once again for reporter, what would be the most important parameter to affect and why?
Most important.
Yes.
As the angular velocity is very big, this will be very small, right? Okay, so if the angular velocity is big enough, we ignore this, and we only consider the dm over dt, and we write as rho pi r naught squared, and
So you just let me know what is
the depth, the central part of the depth and the radius.
I think it would be the angular velocity that affects the most, because in our experiment we did many parameters that will affect pump speed after we did the normalization of our
So you
data.
disagree with
Yes, I agree. I disagree with it. I think that angular velocity affects the most.
I agree with the opponent, and I disagree with the.
And I have one additional question for the reviewer is about you talking about the deviation. So why do you think is so important? Why do you think is important?
Because when there's deviation, they call it energy, and then might be energy difference.
Okay, sorry. So just 1 minute to jury to calculate the score. Okay, let's start from the reporter. So now is the score for reporter. It's 7, 8, 7, 8, and 7. So next would be the score for the opponents. 7, 7, 8, 8, 6. Finally would be the score for the reviewer. So it's 5, 4, 6, 6, 5. Thank you very much. Thank you. So now the section.